How will it all end? It's a question we humans have asked for millennia. We've pondered it around campfires, written it into our myths, and debated it in our halls of science. But we're not just talking about our own lives, or even the life of our planet. We're talking about everything, the whole cosmic shebang. Will the universe go out with a bang, collapsing back on itself in a fiery big crunch? Or will it be something quieter, something slower, something colder? This is perhaps the grandest question we can ask. A story written in the laws of physics, unfolding over trillions upon trillions of years. It's a story about the ultimate fate of every star, every galaxy, every atom. The universe we know is a place of spectacular energy and breathtaking structure. We see brilliant nebulae birthing new stars. We see massive galaxies spinning in a celestial ballet. Energy is concentrated in brilliant, hot points of light, while vast, cold emptiness stretches between them. It's a universe of contrast, of hot and cold, of order and chaos. But the laws of physics tell us this state of affairs can't last forever. Think about an ice cream cone on a hot summer day. You start with a beautifully ordered scoop of cold, solid ice cream. It's a concept that governs everything from your morning coffee to the fate of the cosmos itself. Let's rewind the cosmic clock. All the way back. About 13.8 billion years ago, the entire observable universe, all the energy, all the matter, all the space was compressed into a point of unimaginable density and heat. This was a state of incredibly low entropy. Then, bang! The universe began to expand, and it's been expanding ever since. In the first few 100,000 years, the universe was a super-hot, opaque fog of plasma. Eventually, electrons combined with nuclei, forming the first atoms. That moment, recombination, made the universe transparent. Light was set free. We see that leftover light today as the cosmic microwave background. As billions of years rolled by, gravity pulled matter together. Giant gas clouds formed, which collapsed to ignite the first stars. Those stars were pockets of low entropy. They took disordered hydrogen and helium and, through nuclear fusion, forged heavy elements while releasing concentrated energy. But look closer. Every photon streaming from a star carried energy out into the void, spreading it thin and increasing the cosmos's disorder. The universe is expanding, driving entropy. Space gets bigger and energy has more room to dilute. Endless expansion gives entropy room to spread energy thin, spreading all energy and matter as thinly as possible. So if the universe keeps expanding and entropy keeps increasing, where does this all lead? This brings us to the ultimate conclusion: heat death of the universe. The name sounds dramatic, like a fiery apocalypse, but the reality is the opposite. Not fire, ice. Imagine the universe as a vast room. At the start, a roaring fireplace, the stars, and icy windows, deep space, huge temperature difference, air currents flow, things happen. Fast forward, the fire burns out. Warmth spreads evenly. Icy windows warm a tiny bit. The room is the same lukewarm temperature. No hot spots, no cold spots, no air currents. Perfect, unchanging stillness. That is heat death. Why do scientists favor this fate? It's the logical endpoint of observation. Expansion isn't slowing, it's accelerating. An unknown force, dark energy, pushes everything apart faster. So, no big crunch. The universe gets bigger, colder, emptier. Endless expansion gives entropy room to spread energy thin, spreading all energy and matter as thinly as possible. In maximum entropy, all processes that make the universe alive will cease. With no temperature differences, no energy flow. Without energy flow, no work can be done. Stars can't shine, no fuel, no cold sink to radiate into. Life that processes energy becomes impossible. Even chemical reactions would grind to a halt. The final permanent end of time as we know it. For the next few trillion years, the universe will still look somewhat familiar. Stars will continue to be born, burn, and die. But as the gas clouds needed to form new stars are used up, star formation will slow to a trickle, and eventually stop altogether. This is the end of the stelliferous era, the age of stars. The universe will grow dimmer. The brilliant spiral galaxies will fade their last stars. The small, long-lived red dwarfs finally exhaust their fuel and become cold, dark cinders known as black dwarfs. The universe will then be a graveyard of stellar remnants, a vast, dark expanse populated by black dwarfs, neutron stars, black holes. The planets that once orbited these stars will be frozen, lightless husks, drifting in the eternal gloom. The galaxies themselves will have dissolved. The accelerating expansion of space will have pushed all other galaxies so far away, their light no longer able to reach us. our local group of galaxies will be the only thing left, a lonely island of dead stars in an otherwise completely empty void. The sky for any observer who might be left would be utterly and completely black. But even in this profound darkness, the work of entropy is not yet finished. Over truly unimaginable timescales, even these stellar corpses will decay. Quantum physics suggests that protons are not truly stable. Matter itself will dissolve. This leaves only the most stable objects in the universe, black holes. For a time, they will be the kings of the cosmos, the last bastions of structure. They will slowly grow by swallowing up the stray particles. But even black holes are not forever. Thanks to a process known as Hawking radiation, they too will slowly evaporate. The smallest black holes will go first, the supermassive ones at the centers of galaxies will be the last to go, taking perhaps 10 to the 100th power years, a Google years, to finally disappear in a final faint pop of radiation. And with the death of the last black hole, the universe enters its final stage. After the last supermassive black hole has evaporated, the universe will be almost perfectly empty. Imagine a cosmos so vast and so empty that the average distance between particles is measured in light years. Photons, neutrinos, electrons, positrons, all just flying aimlessly through the ever-expanding void. There are no structures left, no stars, no planets, no atoms, not even black holes, just a diffuse, cold, and eternally darkening mist. The temperature of this universe will be infinitesimally close to absolute zero, the theoretical point at which all motion ceases. The energy that once powered suns and forged galaxies will now be spread so thinly it is effectively useless. This is the state of maximum entropy. The cosmic room is now at a uniform temperature. The story is over. The curtain has fallen. The great cosmic engine has finally and irrevocably run down. Now, it's important to remember that this projection of heat death is based on what we know right now, and honestly, the history of science is a history of being surprised. What if there are new laws of physics we haven't discovered yet? What if our understanding of dark energy is incomplete or just plain wrong? Perhaps dark energy isn't a constant. Maybe it will decay or reverse itself, causing the universe to stop expanding and begin collapsing, leading to that fiery big crunch after all. One is the idea of a Boltzmann brain. Over an almost infinite amount of time, particles could randomly assemble into a complex ordered structure. Then there's the idea of a cyclical universe. Perhaps the end is also a beginning. Some cosmological models propose that the universe could rebound. Maybe, once the universe reaches maximum entropy, some unknown process could trigger a new Big Bang. Or perhaps our universe is just one bubble in a multiverse of countless other universes, each with its own laws of physics. These are ideas on the very fringe of theoretical physics. They remind us that the book of the cosmos is far from closed. What seems like an inevitable ending today might just be the setup for a final act surprise that we can't yet imagine. Thinking about the end of the universe can feel distant, abstract, and maybe even a little pointless. After all, we're talking about timescales so vast they defy human comprehension. Our lives are less than a blink of an eye in this cosmic saga. So why should we care? We should care because this story gives us the ultimate context for our own existence. It frames our brief shining moment in the cosmos and imbues it with a profound sense of preciousness. We are alive now, here, in the stelliferous era. We are living in the universe's glorious, vibrant youth, when the sky is ablaze with 1 trillion galaxies and the cosmos is teeming with energy and potential. We are the lucky ones. We get to exist during the cosmic springtime, not in the long, cold, eternal winter that may follow. We are the universe's conscious witnesses. We are stardust that has woken up with the ability to piece together the story of our cosmic home. The cosmos is telling its own story through us. So as you go about your day, look up. Remember that the light hitting your eye is part of a grand, unfolding drama that began 13.8 billion years ago and is heading towards a truly epic conclusion. What do you think happens after the lights go out?